Hello everyone, thanks for joining me. I'm John Doherty. This video is a little bit philosophical in nature, but I think quite important. What we'll do over the course of this video is start by looking at a simple model and then draw some important conclusions from that simple model regarding decision support modeling in general. Everything we talk about in this video is also recorded in written form in a GMDSI monograph, which can be downloaded from the GMDSI website at this address. We focus or develop a narrative about the journey of information, and I think this is a good way to look at decision support modeling because it does provide insights that are difficult to achieve in any other way. Insights which we will develop through this video and then draw some much more general conclusions. So we'll start off with a simple model, a model that is about as simple as it can be, but even though it's simple, it does have some resemblance to the sort of decision support models that we use in everyday groundwater modeling practice. There's a little bit of mathematics, don't be daunted. This mathematics, you don't have to follow every bit of it, just the meaning of it. And this mathematics will take us on our own journey to an understanding of how information is harvested and how it flows through a model, through history matching and conveyance of information to predictions that we care about. Once we've got those insights, we then draw some conclusions that I think are of fundamental importance to decision support modeling in general. In particular, we'll focus on whether the traditional way of harvesting information through adjusting model parameters is always the best way to harvest and deliver information. I'll suggest to you that it's not always the best way and that there are some instances where there are better ways to do this thing. But before we start talking about any of that, let's remind ourselves of why we do decision support modeling. What are the goals of decision support modeling? This is discussed widely in other GMDSI videos and monographs. Our job is to make forecasts of future system behaviour, often under conditions which are very different from those which a groundwater system had in the past. Those predictions will often, but not always, be accompanied by uncertainty. Part of our task is to quantify that uncertainty. Part of our task is to reduce that uncertainty. Put together, our task in doing decision support modeling is to harvest information from wherever we can find it and to deliver it to where information is needed in order for someone to make a decision. Some look at decision support modeling as trying to achieve a thing called integrity of simulation. As is discussed in other monographs and videos, I don't think this is something we can really achieve, and often attempts to achieve it actually get in the way of achieving the thing we must achieve, and that is harvesting and delivery of information to those who need it. So with that in mind, let's focus on information and see what we can learn from a very simple model. So let's look at this model. Here it is. In this model we have groundwater flowing into the right-hand side of a confined aquifer system. The aquifer is comprised of two blocks with two resistances, R1 and R2. Flow is unity. That makes the maths very easy. We have a single observation at the right-hand end of the system. This is our calibration data set, our history matching data set. This is what we use to reduce the uncertainties of the estimates of the two resistances and of the predictions to which they're sensitive. Now, in other GMDSI monographs, we've used this equation to describe how a model acts when it's been calibrated. This equation says that the action, what we observe in the field, is equal to the action of a model on its parameters plus measurement noise. This is a linear equation. Z matrix here is a matrix, therefore the system is linear. K is a vector comprised of a number of parameters. Now, in normal everyday modelling practice, we haven't got a linear system, so we modify our use of this equation to accommodate nonlinearity. In the present case, the system is linear. No accommodation is necessary. So to use this equation for our simple model, it actually turns into the equation here that I'm indicating. The head on the right-hand side of this model domain is equal to the sum of the resistances plus measurement noise. Don't forget, the flow is unity, that's why we can just sum these resistances. So I've written it here as a matrix on vector equation. We're going to be looking at two predictions. The first prediction is the head in a well that's situated just at the right-hand end of resistance number 1. Now, in other GMDSI monographs, we use this type of equation to characterize a model that's making a prediction. Y is the sensitivity of the prediction to model parameters. In the present case, that's particularly simple. The value of S1 is simply equal to the resistance R1 because flow through the model domain is unity, and it can be written using this very simple matrix on vector equation. Our other prediction is the head in the original observation well if the flow into the right-hand end of the model domain is doubled. In this case, this value of this prediction can be calculated as twice R1 plus R2, twice because flow has now been doubled. Now, in this and in all other modelling exercises, we assume that we don't go into the modelling process completely ignorant. We know something about the system. We know, well, we can characterise it probabilistically. We know, for example, prior expected or prior mean values of parameters. We have, for example, a covariance matrix which expresses the prior probability distribution of model parameters. So we'll assume that we have that same information here. We'll characterize our prior mean resistance values as R1M and R2M. And here is our covariance matrix, our prior parameter covariance matrix, with the individual elements recorded within the matrix. This is the variance, the prior variance of the first resistance, the prior variance of the second resistance, and this is the cross covariance between the two resistances, if in fact there is any correlation between them. Remember, variance is the square of standard deviation. Now, intuition tells us that there's something fundamentally different between these two predictions. Intuition tells us that if we have a single head observation here, we're not going to be able to say what the value of the head is somewhere between the right-hand end of the system and the left-hand end of the system. Intuition tells us that there are quite a number of values that this head may take, and they will depend on the values for R1 and R2, which we don't know. We know their prior values, we know their covariance matrix, but we don't know the actual values for resistance number 1 and resistance number 2. Therefore, intuition tells us this prediction is going to be uncertain, and that's going to be an outcome of the ill-posed nature of the inverse problem that we are solving when we history match this model to this single head observation. Prediction 2 is different. Yes, there's going to be uncertainty associated with R1 and R2, but a measurement of head here when the flow into the right-hand side of the system is 1 tells us a lot about what the head in the same place is going to be when the inflow into the right-hand end of the system is 2. So these predictions are different. Intuition tells us so. Let's formalize that using mathematics and then use that mathematics to draw some more general conclusions. But first, let's look at the theory that we'll use for history matching our little model. This is the same theory as that used by PEST and PEST++. We can approach this theory from a number of points of view. We'll approach it from a Bayesian point of view. Consider a random vector z comprised of two subvectors x and y that are correlated with each other, represented them diagrammatically here in this two-dimensional picture. Now, the mean of xy, that is, the mean of z, is given by the mean of x and the mean of y, the one vector on top of the other comprising the total vector mean of z. Let me denote the covariance matrix of z, that is, the covariance matrix of xy, in this way using this green equation. Now here I've partitioned that matrix into CXX, which gives the prior covariance matrix of x, the covariance matrix of y, and here these are the terms, the cross covariance terms. These are important in the conditioning that we will do shortly. Suppose now that I obtain perfect knowledge of y, and I'm going to encapsulate the values of that perfect knowledge in a vector named yc, c for conditioning. I'm also going to suppose that xy has a multi-Gaussian probability distribution. So yc now contains the values that I have just acquired of y. And because x and y have cross covariances, knowing something about one is able to tell me something about the other. The posterior or the conditional mean of x is given by this blue equation. Note the importance of the cross covariance terms. The conditional covariance matrix of x is given by this second blue equation. Note once again the importance of the cross covariance terms. So, as I mentioned, this is called conditioning if we're coming at it from a Bayesian perspective. Because x and y are correlated, knowing one tells me something about the other. I now have a conditional mean of x because I suddenly know y. I now have a conditional covariance matrix of x in which the uncertainty is reduced because of the knowledge that I've acquired of y. So we're going to base everything that we do from now on just on these simple principles. So let's apply this theory to our simple model. Firstly, focusing on its application to making prediction S1. This is the slide that we had previously. Let's take some equations and implement the theory that we've just seen. First, let's write these two green equations. This is saying nothing more than the vector R is the identity times matrix times the vector R. This bottom equation is the same as this equation up here. Let's stack one on top of the other in a single matrix equation to obtain the yellow equation. Now, the equations we saw previously required covariance matrices, so let's build them. We've got an equation here. We need a covariance matrix of this vector R1, R2, H. To build that, we use a simple formula for propagation of variance that has been discussed in other GeoMDSI videos. If X is a random vector, A is a matrix, then Y is a random vector. The covariance matrix of Y is then given by this equation. Let's apply it to the yellow equation. If we do, we obtain the top yellow equation. Now let's actually put the individual elements of this covariance matrix in place in the green equation and then multiply out. And here we have the individual elements of the covariance matrix of the vector R1, R2, H. Note, by the way, that this term here is equal to the variance of R1 plus R2, the sum of the two resistances that occupy the model domain. So now we have a covariance matrix that links our parameters to the measurement that we are using to condition the parameters. We have what we need to now history match our model to condition R1 and R2, our parameters, by the single head measurement which comprises the entirety of our calibration data set. So let's do that. We will partition this matrix into submatrices which are the same as the matrices that appear in these equations. This allows us to use these equations to do the conditioning. What we desire is posterior means of the vectors of the parameters R1 and R2 conditioned by H, and eventually the posterior uncertainties of these parameters. So we partition this matrix so that we can apply these equations. Let's apply this equation first to obtain the posterior mean of our two parameters R1 and R2. So this is like what we obtained from model calibration, the posterior means of our parameters. So if we apply that equation here, the blue one with the rectangle around it, to the equation on the previous slide, this is what we obtain for the posterior mean values of R1 and R2, our two resistance parameters. Now, just to make things a little bit clearer, let's make some substitutions. Firstly, the head measurement is equal to R1 plus R2 plus epsilon. The mean head, the prior mean head, is equal to the sum of the prior mean values of R1 and R2. Also, just to make the following equations a little bit simpler, let's work in terms of perturbations from the prior mean. I'm going to define P1 as equal to R1 minus its prior mean, P2 as equal to R2 minus its prior mean. If I do that, make the substitutions into the blue equation, I obtain these two yellow equations. Here we have the estimated values of parameter perturbations from their prior means, the calibrated values of parameter perturbations from their prior means. And recall, because of the nature of our first prediction, this is also the perturbation of prediction number 1 from its prior mean. Now let's just focus then, because this is what we're concerned about at the moment, prediction number 1. Let's focus on this first resistance, or its perturbation of this first resistance from its prior mean. Here is the equation written explicitly for that particular perturbation, and let's draw some conclusions from this equation. Conclusion number 1. If measurement noise is very large, that is, this term here is large, the estimated value of R1 is its prior mean. Well, that's not surprising. If our measurement is drowned in noise, it doesn't tell us anything. Point number 2. The estimated value of P1, and hence R1, is influenced by all the media through which water flows. Now, when we're just looking at prior expected values, the expected value of our prediction is simply equal to the expected value of this resistance. In fact, the expected value of this resistance is equal to the expected value of this resistant. Once we've history matched, things are a little different. The expected value of this resistant is now a little bit more complicated, and it is calculated from the actual values of the resistances even though we don't know what these are. It is affected by both of them. It is no longer affected only by itself. Point number 3. The estimated value of P1, and hence R1, and hence prediction number 1, is also influenced by the prior uncertainties and covariances of all the media through which information flows. Point number 4. If the prior uncertainty of R2 is large, this term, the estimated value of R1 is its prior mean. Therefore, all of the information contained in the single head measurement is absorbed by R2. Point number 5 from this equation. If the prior uncertainty of R2 is small, the estimated perturbation of R1 from its prior mean is equal to the sum of the perturbations of R1 and R2 from their prior means. Therefore, all of the information contained in the single head measurement is absorbed by R1. This has repercussions. We've represented R2 here as an upstream resistance. What if it was upstream but encapsulated in a boundary condition? And what if we said that the hydraulic properties of that boundary condition are certain, as is often done in groundwater modelling practice? We hardwire properties of boundary conditions into the model. We don't recognise that they may be uncertain. So if R2 is in fact a prior boundary condition, a model boundary condition whose value is wrong, then the value estimated for R1 compensates for this error without model to measurement misfit being compromised. We'll return to that in a moment. But before we do, let's look at posterior uncertainties. So here's our covariance matrix of R1, R2, H, once again partitioned in a way that we can use these equations. Now let's use the second of these equations. When we do, we obtain the green expression for the posterior covariance matrix of our parameters. If we multiply out all these terms, we obtain the yellow equation in which each element of the posterior covariance matrix is made explicit. Let's focus on this term. This pertains to R1, and of course prediction number 1 pertains to R1. This is really the focus of our attention, so let's write explicitly the posterior uncertainty variance of resistance R1. It's equal to its prior variance minus a number that is an outcome of the information that's available in the history matching data set. So what conclusions can we draw from this equation? Well, the first conclusion, if measurement noise is large, the posterior uncertainty of R1 is reduced very little from its prior. Once again, this is not surprising. If a measurement is drowned in noise, it doesn't help us much. Point number 2. If the prior uncertainty of R2 is large, that's this term, then the posterior uncertainty of R1 is reduced very little from its prior. Point number 3. If the prior uncertainty of R2 is small, then the posterior uncertainty of R1 is also small. Point number 4. If R1 and R2 have roughly equal prior uncertainties, and there's a high degree of prior statistical correlation between R1 and R2, that's this term here, then the posterior uncertainty of R1 is small. Let's just put these conclusions into something that a little bit more approaches plain English. The ability of information to reduce uncertainty of a target prediction is diminished if information encounters uncertainty on the way to its target. The information gets lost along its way to that target. If R2 is an erroneous boundary condition, we talked about that before, or another aspect of a model to which zero uncertainty is attributed by the modeler, then not only does R1 compensate for this error, it appears to have little uncertainty. User assignment of spatial parameter correlation is important information. It can reduce uncertainties that field measurements on their own cannot reduce. These are important insights. But let's framing it according to the narrative that we're trying to develop here of the journey of information. The path along which information must travel has many dangers. Uncertainty attracts information. If information encounters uncertainty along its journey, it may not arrive at its destination. If uncertainties along the path that information must travel are ignored, information has nowhere to go. It's like a light with no surface to illuminate. Finally, careful design of prior parameter probability distributions may reduce key predictive uncertainties by complementing information contained in measurements of system state. It is clear that the path along which information must travel must be carefully prepared by a decision support modeler. Preparation of a path for this journey is one of our most important tasks in designing how we will model, what the model's parameters are, what the prior probability distributions associated with parameters are. All of these things must be given careful attention. Mistakes in any of these things could cause problems in the parameters that we estimate, the uncertainties that we attribute to those parameters, and the predictions that we make with our history-matched model. Alright, now let's turn our attention to prediction number 2. Recall that prediction number 2 is the head in the right-hand well when inflow to the model is doubled. It's calculated as twice the sum of the two resistances. Calibration estimated deviation from its prior mean is twice the sum of the two deviations from their prior mean of each of these two resistances. Now recall from just a moment ago that we calculated the posterior perturbations from their prior means of R1 and R2 using these yellow equations. Now let's sum them so that we can obtain the value of prediction number 2. Let's sum them and multiply by 2. If we do that, we obtain for the posterior expected value of prediction number 2 this expression here. And recall that this is the prior uncertainty variance of the sum of R1 plus R2. So what does this equation tell us? It tells us that if measurement noise is large, the estimated value of prediction number 2 approaches its prior value. Well, again, no surprises here. If there's a lot of noise, measurements don't mean much. They can't tell us much. But secondly, it tells us that if measurement noise is small, the estimated value of prediction number 2 approaches its true value. History matching does not introduce new parameter dependencies for the prediction as it did for prediction number 1. So prediction number 2 is very different from prediction number 1. Hence, The single head observation is directly informative of prediction number 2, even though this information passes through two parameters that are individually only partially informed, and whose uncertainties may be high and possibly incorrectly evaluated. The integrity of this information therefore remains intact, regardless of problems that it may encounter along its journey. Now let's look at the posterior predictive uncertainty of prediction S2. S2, we know, is twice the sum of the individual resistances, twice because we've doubled flow of water through the system. Recall also the driving equation of our system. Put them together and turn them into a matrix on vector equation, and we have the yellow equation. Propagation of variance, as we did before, we obtain a covariance between the head and the prediction. We need this covariance because this allows us to apply the conditioning equations that we discussed before. If we multiply out this equation, we obtain the Brown equation. Simplify a little, recognizing that this sum here is equal to the variance of the sum of the two resistances, and we have a simple expression for the covariance between H and S2. Using this covariance matrix gives us the ability to apply the conditioning equations we saw before. Now I can calculate the posterior covariance matrix for S2, but because S2 is a single number, this just becomes the posterior variance for prediction S2. So if I apply this conditioning equation to this covariance matrix, I obtain the green equation for the posterior variance of prediction S2, from which it follows that as measurement noise approaches 0, the uncertainty of prediction number 2 approaches 0. Non-uniqueness of the inverse problem does not affect my ability to make this prediction. Point number 2, information therefore arrives at this prediction without any loss of integrity. It is not degraded along its journey. The posterior uncertainty of prediction 2 depends only on its prior uncertainty and on measurement noise, regardless of the complexity of the system. So, continuing on our information as a journey narrative, for some destinations, the journey that information takes is not hazardous. Sometimes, different fragments of the same information take different paths, but arrive at the same destination together. This is because there may be some model predictions that are directly informed by measurements of system state and fluxes. These predictions may be sensitive to parameters whose posterior uncertainties are large, whose values may have been corrupted by model defects and by errors in user-ascribed prior uncertainties. Nevertheless, the integrity of these predictions is not affected by these errors, nor are their uncertainties diminished by apparent uncertainties of the predictions to which they are sensitive. Alright, that ends the mathematical section of this video. Let's now try to give a pictorial representation to what we've just learned, and then try to draw some conclusions that are very important for decision support modeling practice. So, this is just a picture, and like any picture, it has its deficiencies. Still, I'm hoping that it gives us some insights that we can use to draw some pretty important conclusions. So, as we started off by saying at the beginning of this video, the task of decision support modeling, or part of the task of decision support modeling, is to harvest information from data where it resides. and to deliver that information to predictions that have management consequences. So here's data, and picture information as a beam of light. That information enters a model. And decision support modeling here is busy harvesting that information. And notice I'm using modeling as a verb and not a noun. This is something that's discussed in other GMDSI videos. It's a process rather than a deliverable. And here it is doing what decision support modeling must do: harvest information from data. Now that information may inform not one but many parameters, as we saw in our previous little model that we talked about earlier in this video. Now for some lucky predictions, that information is recombined in order to inform a prediction of interest. In that case, errors that may be accrued through separating this information out and to be borne by the different parameters which carry that information, they're all forgotten as that information is recombined to make this prediction. Errors in separating information are left behind as it recombines to make this type of prediction. This is a happy prediction, a happy situation. But there are many other circumstances where the situation is not as happy. Data provides information that flows to many parameters. In assimilating that information, the model attempts to separate out that which is pertinent to a prediction of interest and that which is not. And we have just seen that that process of separation of information is fraught with many difficulties. There are many places along that path that information must take where things can go wrong. So if only part of that information is of use to us, this prediction may be compromised by the information separation process that decision support modeling is carrying out. And compromise means it may be biased. Its uncertainty may be overestimated or underestimated. So as we said, the ability of a model to separate information properly and deliver it to a prediction may be compromised by many things. We've seen model structural imperfections, model parameterization imperfections, errors in characterizing prior parameter probability distributions. And the thing is, this gets worse with the more complicated is our model and the more complicated is the parameterization scheme that we give it. If we make our model complicated, we're trying to represent structural detail, parameterization detail. But we don't know the details of the detail. Hence, should that detail, should that parameterization detail, should that structural detail be represented stochastically? Probably it should, but often it's not. And even if we do try to represent give parameterization detail a proper stochastic representation, how difficult is it to get that stochastic representation correct when parameters have to be adjustable in order to harvest information and in order to quantify the repercussions of lack of information? Making them adjustable means they're going to be somewhat abstract, a little bit different from the detail that we're trying to represent in a complex model. And the more abstract they are, the more removed are they from reality, and the more difficult it is to apply the correct prior probability distribution to those parameters. So this tells me that there is an upper limit on the complexity of a workable, adjustable decision support modeling parameterization scheme. If our task or the task of the model is to separate information into that which is relevant to a prediction and that which is not. We have already seen that there are many places where that can go wrong, and we have to pay particular attention to making structural and parameter details correct and probability distributions associated with parameter details. There comes a point with increasing model structural and parameterization complexity where this is not going to be possible. And this has important consequences for the way that we engage in decision support modeling. Can this problem be alleviated? Well, there are a couple of ways which it can, some more effective than others, depending on our modeling circumstances. The first option is to be very careful in how we pose the history matching problem and in how we formulate the objective function that we minimize when we harvest information from data. The idea here is to search for ways in which we can separate out prediction-salient information from non-prediction-salient information before it actually enters the model. So what we're looking for is a way that we can filter out information that informs parameters that are not salient to a prediction, because we've seen how that information separation process is easily corrupted, especially in a complex model. If we can avoid the deleterious effects of information splitting, then maybe we're ahead, because we can harvest only the information that we need and direct that information to predictions of management interest. And at the same time, if we can do that, perhaps we can simplify a model. We can remove from that model parameters which are not prediction salient. This may allow the model to run faster. It may allow the model to be simpler. Perhaps it'll be more numerically stable. Perhaps the whole information harvesting process will go much more smoothly. So what we want to do is go from this to this. So how can we do that? Well, I think there are many situations where we can achieve something like this. For example, suppose we have to make predictions that are dependent on differences. For example, difference of a head in one layer from that in another, or flow between one aquifer and another, or seasonal differences in heads. Then if we make sure that perhaps we can formulate the objective function that we use in the history matching process such that differences that are pertinent to the predictive differences, that historical differences, are accentuated. And therefore, the model has a direct line of sight to the information which is most pertinent to the predictions that it has to make. There may be other circumstances where we want to predict, for example, the final equilibrium state of a system. In that case, perhaps we want to accentuate steady state observations because they're most rich in information pertaining to equilibrium states, the properties of the model that transmit water. So, some information may be lost by formulating an objective function that just accentuates certain parts of system behavior over another. But at the same process, the information that may have been lost by perhaps not allowing all information to enter a model may have been corrupted anyway, and we've seen how it can be corrupted. All of this falls under the umbrella of decomposing the problem. And in fact, decomposing the problem is a subject matter of other GMDSI monographs and videos. Or can we do something completely different? Can we look at other ways to harvest information from data and build as direct a path as possible for that information to the prediction that it has to make? So, continuing our pictorial representations, can we take information and filter it such that we retain only that which is pertinent to one or a number of predictions of interest? So, and in doing so, can we remove from consideration those aspects of the data that are not prediction pertinent and that may, if we're harvesting that information and storing them using parameters, may distort our ability to make important model predictions? If we're trying to do this using complex parameterization schemes in complex models. Now, it turns out there is a way that we can do this, and that way is data space inversion. There, it reasons in ways that we discuss in other GMDSI videos and tutorials. We replace our complex model with complex parameterization scheme with a statistical model with a simple parameterization scheme. That statistical model is trained to link the measured past to the managed future by running an arbitrarily complex numerical model many times using different realizations of parameters and perhaps even model structures. However, we do not adjust those parameters. Instead, we train the statistical model, and information harvesting is carried out using that statistical model. This can go a long way toward alleviating the problem of information corruption that occurs when information's journey has to be routed through adjustable parameters and complex structure. So, taking all that we've just said, now let's try to draw some conclusions that pertain to how we do decision support modeling in the real world. What is the best way to extract information from data and deliver it to a prediction? That, after all, is what decision support modeling is all about, as we said way back at the beginning of this video. So I'm going to summarize my conclusions in a graph. On the x-axis of this graph, we have decision pertinent information content of history matching dataset. This can vary between 0 and 1. Where it's 1, a prediction is pretty much data driven, entirely informed by the history matching dataset. Where it's 0, I either have no data to history match against, or the information content of that history matching data set is of no relevance to a prediction I care about. On the y-axis, I have model complexity. Now, in other GMDSI manuscripts, we separate model complexity into parameterization complexity and structural complexity. Here, I'm going to be a little bit more vague than that. Just complexity, which it will be implied is both parameterization and structural complexity. So let's look at the right side of this area here. This is where I can use parameters to extract information from data and convey it to predictions. Right over here, where my predictions are data driven, I can use a structurally simple, parametrically complex model. Fit first, ask questions later. If some of the parameters are a little bit strangely valued given the hydraulic properties that they represent, I don't care too much for reasons we've already talked about. I've extracted information from the history matching dataset. That information coalesces again. It remains intact. It does not suffer from its journey through those parameters because the prediction is data driven, fully informed by the calibration data set. As I move further over to the left though, separation of information that is salient to a prediction from that which is not salient to a prediction becomes more and more important. Here, for reasons that we've already discussed, I've got to be careful. My structure has to have integrity. My parameters have to have integrity. The prior probability distribution of the parameters has to have integrity. It gets harder and harder to ensure this as I move to the left along this graph. Then I get to a place where I can't guarantee that the parameters are indeed the best mechanism for extracting and conveying information. It could be that that information suffers too much damage along the way to predictions that I care about. Here then, I've got a choice. I could follow the red line. I could say I'm not going to try to extract any information from the history matching data set. It's not worth it. The chances of its corruption are too great. If I do worst case analysis, and if on the basis of demonstrably worst case analysis I can reject the hypothesis that there's going to be a bad management outcome, well, that hypothesis is rejected. So this then can be my decision support strategy. It'll be a lot cheaper than trying to build a complex model, and under certain circumstances will be just as effective. Or I could say that my prediction is complicated. It depends on complicated aspects of the system, complicated distribution of hydraulic properties, maybe distributions of fractures or other things that are hard to represent parametrically, and attempts to represent them parametrically, especially if those parameters, as parameters always are, especially if those parameters have to be adjustable, then I run the risk of doing more harm than good trying to extract information from my historical data set and conveying it to a prediction using abstract adjustable parameters which may be inappropriate for conveying what could happen in the future under a new groundwater management regime. In that case, I can be stochastic and I can be as complicated as I like. I do not have to adjust the parameters. The model may take a long time to run. Parameters may be categorical rather than adjustable. If there's no information in the history matching data set, then I can just do prior Monte Carlo analysis of the prediction of interest. If there is information, I can use data space inversion. And data space inversion can be used not just in this white area, but also in this yellow area. There's no reason why in this area here I can't harvest information from data using parameters and harvest information from data using data space inversion, and that way I've got a check. One can check on the reasonableness of the other, and if they agree, I've got a lot more confidence that my predictions do not suffer bias and that uncertainties that I quantify are correct. In the end though, everything depends on the prediction that I'm going to make. And everything depends on harvesting information and conveying it to that prediction. As other GMDSI monographs and tutorials point out, the prediction is critical on the way we design and deploy decision support modeling. That's always been the case, and that process is a little bit the thought processes behind how we select a way of doing this is encapsulated, to some extent at least, in this graph, which I hope helps you to decide how to go about your own decision support modeling jobs. So that brings us to the end of this video. Thanks for watching, and see you next time.